Look up at the night sky right now if you can. Find a single star. Any star will do. Focus on that tiny point of light piercing through the darkness. What you're seeing at this very moment is nothing short of miraculous. That gentle photon landing on your retina has traveled across unimaginable distances, through the cold vacuum of space, for years, decades, perhaps centuries, just to reach your eye. It began its journey in the nuclear furnace of a distant sun, born from the collision of atomic nuclei in temperatures that would vaporize our entire planet in an instant. But here's what's truly extraordinary about this moment. That single particle of light that just triggered a cascade of electrical signals in your brain carries with it the most fundamental mystery in all of physics. Is it a wave rippling through space like a stone thrown into a cosmic pond? Or is it a particle, a tiny bullet of energy racing through the void? The answer, as we'll discover together, is both more beautiful and more strange than either possibility alone. This is the story of light, not just the light we see, but light in all its forms, from the radio waves carrying signals across continents to the gamma rays born in the death throes of stars. It's the story of how we came to understand that light is both the messenger and the message, both the observer and the observed, both wave and particle, in a cosmic dance that has puzzled the greatest minds in human history. Tonight we're going to follow that photon's journey from its birth in stellar fire to its arrival in your eye. We'll explore how light reveals the deepest secrets of reality itself, and how our understanding of light has revolutionized not just physics, but our entire conception of what it means to exist in this universe. So settle in, let your mind wander among the stars, and prepare to see light as you've never seen it before. What we think we know about light seems so simple, so obvious. We flip a switch and darkness becomes brightness. We step outside and the sun warms our face. We look in a mirror and light bounces back to show us our reflection. Light, in our everyday experience, is just there, as natural and unremarkable as the air we breathe. But this casual familiarity masks one of the most profound truths about our universe. The light we see, the colors that paint our world, from the deep crimson of a sunset to the brilliant azure of a summer sky, represents only the tiniest sliver of a vast electromagnetic spectrum that stretches far beyond the limits of human perception. Imagine, if you will, a cosmic piano with keys extending infinitely in both directions. The visible light we know and love occupies just 7 keys in the middle of this infinite keyboard. To the left of our visible keys, stretching toward lower frequencies and longer wavelengths, we find the infrared radiation that we feel as heat radiating from a warm fire. Move further left, and we encounter microwaves, the same energy that heats our food, but also carries the faint echo of the Big Bang itself across the cosmos. Further still are radio waves, some with wavelengths longer than football fields, carrying everything from your favorite music to the whispered signals from galaxies billions of light years away. Now turn your attention to the right side of our cosmic keyboard, toward higher frequencies and shorter wavelengths. Just beyond the violet edge of visible light lies ultraviolet radiation, the invisible energy that can both give you a suntan and reveal hidden patterns on flowers that only bees can see. push further right, and we enter the realm of X-rays, electromagnetic waves so energetic they can pass through flesh and bone to reveal the hidden architecture of our bodies. At the far right edge of our spectrum lie gamma rays, born in the most violent events in the universe, carrying energies that dwarf anything we can create on Earth. All of this, from the gentlest radio whisper to the most violent gamma ray burst, is light. It's all the same fundamental phenomenon, differing only in the energy each photon carries, the frequency at which the electromagnetic field oscillates, the wavelength of the cosmic ripples spreading through space and time. The warm glow of candlelight and the deadly radiation from a nuclear explosion are at their core the same thing, just playing different notes on that infinite cosmic piano. This realization that all electromagnetic radiation is fundamentally the same phenomenon represents one of the greatest unifying insights in the history of science. It tells us that the universe speaks to us in a single language, the language of light, but in dialects spanning an incredible range of energy and scale. The radio telescope listening for signals from distant civilizations, and the optical telescope capturing the beauty of distant galaxies are both, in essence, doing the same thing, collecting light, gathering the electromagnetic messages that the universe has been sending across space and time. But even this grand unification of the electromagnetic spectrum pales in comparison to the deeper mystery that light presents. For when we look closely at light itself, when we try to understand what it really is at the most fundamental level, we encounter a paradox so profound that it shook the very foundations of physics and continues to challenge our understanding of reality itself. The story begins in the late 17th century with two giants of science locked in intellectual combat. On one side stood Sir Isaac Newton, the man who had already revolutionized our understanding of motion and gravity. Newton was convinced that light consisted of tiny particles, what he called corpuscles, streaming through space like invisible bullets. This made perfect sense to Newton's mechanical worldview. Light traveled in straight lines, cast sharp shadows, and could be reflected off surfaces just like bouncing balls. Particles, Newton argued, could explain all of light's observed behaviors. On the other side of this great debate stood Christian Huygens, a brilliant Dutch physicist who saw light very differently. To Huygens, light was clearly a wave rippling through space like sound waves through air or water waves across a pond. Waves, he pointed out, could bend around corners, interfere with each other, and spread out as they traveled. While Newton's particle theory struggled to explain these wave-like behaviors, Huygens' wave theory handled them naturally. For over a century, this debate simmered in the background of physics. Newton's immense reputation gave weight to the particle theory, but nagging questions remained. Then, in 1801, a British polymath named Thomas Young performed an experiment so elegant, so definitive, that it seemed to settle the matter once and for all. Young's double-slit experiment was beautifully simple in concept. He shone light through two narrow parallel slits cut in an opaque barrier, then observed the pattern that formed on a screen behind the slits. If light were made of particles, as Newton claimed, you would expect to see two bright stripes on the screen, one behind each slit where the light particles had passed through. But that's not what Young saw. Instead, the screen showed a series of alternating bright and dark bands, an interference pattern that could only be explained if light were a wave. When waves from the two slits met on the screen, they sometimes reinforced each other, creating bright bands, and sometimes cancelled each other out, creating dark bands. It was exactly what you would see if you dropped two stones into a still pond and watched the ripples interfere with each other. Young's experiment seemed to prove conclusively that light was a wave, and for the next century, this wave theory of light reigned supreme. Scientists developed increasingly sophisticated mathematical descriptions of electromagnetic waves, culminating in James Clerk Maxwell's elegant equations that unified electricity, magnetism, and light into a single theoretical framework. The wave theory of light had triumphed, and Newton's particle idea seemed destined for the dustbin of scientific history. But the universe, as we would soon discover, is far stranger than our ancestors could have imagined. The story of light was about to take a turn that would revolutionize not just physics, but our entire understanding of reality itself. The quantum revolution began quietly, almost accidentally, in the year 1900. Max Planck, a German physicist struggling to understand why hot objects glow the way they do, made a mathematical assumption that seemed innocent enough at the time, but would ultimately overturn our entire worldview. To make his equations work, Planck assumed that energy could only be absorbed or emitted in discrete chunks, in specific quantities that he called quanta. Planck himself didn't fully grasp the revolutionary implications of his assumption. He thought of it as a mathematical trick, a convenient fiction that happened to make the numbers work out correctly. But 5 years later, a young patent clerk named Albert Einstein took Planck's idea seriously and applied it to a puzzling phenomenon called the photoelectric effect. When light shines on certain metals, it can knock electrons loose from the surface. But here's the strange part. The energy of these ejected electrons doesn't depend on how bright the light is, but rather on the color of the light. Bright red light, no matter how intense, can't knock electrons loose from certain metals, while dim blue light can do it easily. This made no sense if light were purely a wave, but Einstein realized it made perfect sense if light came in Planck's discrete packets of energy. Einstein proposed that light consists of particles, which we now call photons, each carrying a specific quantum of energy determined by the light's frequency. Higher frequency light, like blue or ultraviolet, carries more energetic photons. Lower frequency light, like red or infrared, carries less energetic photons. When a photon hits an electron in the metal, it's an all-or-nothing transaction. Either the photon has enough energy to knock the electron loose, or it doesn't. There's no in-between. This insight earned Einstein the Nobel Prize, but it also reopened the great debate about the nature of light. Young's double-slit experiment had seemingly proven that light was a wave. Einstein's photoelectric effect seemed to prove that light was made of particles. Both experiments were correct, both conclusions were valid, yet they seemed to contradict each other completely. How could light be both wave and particle? How could the same phenomenon exhibit such seemingly incompatible behaviors? The answer would require a complete revolution in our thinking, a new kind of physics that would challenge our most basic assumptions about the nature of reality itself. This is where our story becomes truly extraordinary, where we step beyond the comfortable world of everyday experience into the strange realm of quantum mechanics, where particles can be in multiple places at once, where the act of observation changes the nature of reality, and where light reveals itself to be something far more mysterious and wonderful than either Newton or Huygens could have imagined. The resolution of the wave-particle paradox wouldn't come from choosing one side or the other, but from embracing both simultaneously. Light, we would discover, is neither purely wave nor purely particle, but something entirely new, something that embodies aspects of both, depending on how we choose to observe it. This principle, known as complementarity, suggests that our classical concepts of wave and particle are simply inadequate to describe the quantum reality that underlies our universe. But to truly understand this quantum nature of light, to follow that photon's journey from distant star to your eye, we need to dive deeper into the electromagnetic spectrum, explore the birth of light in stellar furnaces, and discover how the universe uses light to write its autobiography across space and time. The mystery of light has only just begun to unfold. To understand light truly, we must begin at the beginning, in the heart of a star where temperatures soar to 15 million degrees Celsius and pressures crush matter to densities that would make diamonds seem as light as air. Here, in these cosmic furnaces scattered across the universe, light is born not from electricity flowing through a filament, not from chemical reactions in a flame, but from the most fundamental transformation possible, the conversion of matter itself into pure energy. Picture, if you will, the core of our own sun, a sphere roughly the size of Jupiter, but containing a quarter of the sun's entire mass. Within this stellar heart, hydrogen nuclei, stripped of their electrons by the incredible heat, race through the plasma at speeds that would carry them from New York to Los Angeles in less than a second. Most of these nuclear bullets simply bounce off each other, repelled by the positive electric charges they carry, but occasionally, very rarely, two hydrogen nuclei collide with such tremendous force that they overcome their mutual repulsion and fuse together. This moment of fusion is nothing short of miraculous. Two hydrogen nuclei, each containing a single proton, merge to form the nucleus of heavy hydrogen called deuterium. But the mass of this new nucleus is slightly less than the combined mass of the two original protons. Where did that missing mass go? Einstein's famous equation E=mc² provides the answer. That tiny amount of missing matter has been converted entirely into energy, into the birth cry of a newborn photon. But this photon, this first spark of light born in the stellar core, faces an almost impossible journey. The sun's interior is so dense with matter that a photon can travel only a fraction of a millimeter before colliding with an electron or another particle. Each collision sends the photon careening off in a random direction, like a pinball bouncing through an impossibly complex machine. The photon that began its journey, heading straight outward from the core, might find itself, after a million collisions, heading back toward the center. This is the great paradox of stellar light. While the photon itself travels at the ultimate speed limit of the universe, 300,000 kilometers per second, its random walk through the sun's dense interior means that it might take 1,000,000 years or more to finally reach the surface. The light that warms your face on a summer day began its journey in the sun's core, when our ancestors were just learning to use fire, when the last ice age still gripped the earth. But the story becomes even more remarkable when we consider that not all light is created equal. The fusion reactions in stellar cores produce photons across a wide range of energies, from relatively low-energy infrared radiation to high-energy gamma rays. As these photons begin their 1,000,000-year random walk through the star, they undergo countless interactions that gradually transform them. High-energy gamma rays are absorbed and re-emitted as lower-energy photons. X-rays become ultraviolet light. Ultraviolet becomes visible light. By the time the energy finally reaches the sun's surface, it has been transformed from the violent gamma radiation of nuclear fusion into the gentle mix of visible light, infrared heat, and ultraviolet radiation that we know as sunlight. This transformation tells us something profound about the nature of stellar light. Every photon that reaches us from the sun carries within it the memory of nuclear fusion, the signature of matter being converted into energy in the most efficient process known to physics. When you feel the warmth of sunlight on your skin, you are feeling the direct touch of nuclear fire, the same process that powers hydrogen bombs but tamed and moderated by the immense gravitational embrace of a star. But our sun is just one of hundreds of billions of stars in our galaxy alone. And each of these stellar furnaces produces its own unique signature of light. Massive blue giants, burning through their nuclear fuel at prodigious rates, shine with temperatures of 30,000 degrees or more, flooding space with intense ultraviolet radiation that can ionize gas clouds hundreds of light years away. These stellar behemoths live fast and die young, exhausting their nuclear fuel in just a few million years before exploding as supernovae, their death throes visible across billions of light years. At the other extreme, tiny red dwarf stars with masses less than half that of our sun burn their nuclear fuel so slowly and efficiently that they can continue shining for trillions of years, long after our sun has exhausted its fuel and died. These stellar misers produce mostly infrared radiation, their surfaces so cool that they glow with a dull red heat barely visible to the naked eye. Yet they are by far the most common type of star in the universe, and their longevity means that they will be the last lights burning when the universe grows old and cold. Between these extremes lies a magnificent diversity of stellar types, each producing its own characteristic spectrum of light. Yellow stars like our sun, orange giants swollen to enormous size as they near the end of their lives, white dwarfs compressed to the density of atomic nuclei, neutron stars spinning hundreds of times per second and beaming lighthouse-like pulses of radiation across space. Each type of star tells its story through the light it produces, encoding information about its mass, its age, its chemical composition, and its ultimate fate. But stars are not the only sources of light in the universe, in the violent hearts of galaxies, supermassive black holes, millions of times more massive than our sun, devour matter at tremendous rates, heating the infalling material to billions of degrees and causing it to shine with the brightness of 1 trillion stars. These quasars, as they are called, are among the most luminous objects in the universe, visible across billions of light years of space. Even more exotic are the gamma-ray bursts, brief but incredibly intense flashes of the highest energy light in the universe. These cosmic explosions, thought to be caused by the collision of neutron stars or the collapse of massive stars into black holes, can release more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. The gamma rays from these distant explosions race across the universe at the speed of light, carrying news of cosmic catastrophes that occurred when the universe was young. All of this light, from the gentle glow of red dwarf stars to the violent eruptions of gamma-ray bursts, contributes to what astronomers call the cosmic light background, the accumulated glow of all the stars and galaxies that have ever shone. This background light fills the universe, a faint but measurable reminder of the countless stellar furnaces that have burned throughout cosmic history. And here we encounter one of the most profound insights about light in the universe, because light travels at a finite speed. When we look out into space, we are also looking back in time. The light from the nearest star beyond our sun, Proxima Centauri, left that star over 4 years ago. The light from the Andromeda Galaxy, our nearest galactic neighbor, began its journey toward us 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on the African savanna. This means that the universe is not just a collection of objects scattered through space, but a vast library of light, with each photon carrying information about the time and place of its birth. When astronomers study distant galaxies, they are literally seeing those galaxies as they were billions of years ago, when the universe was young and stars were first beginning to form. The most distant objects we can observe are seen as they were, when the universe was less than 1 billion years old, their ancient light having traveled across space for most of the age of the cosmos to reach our telescopes. But to truly appreciate the cosmic journey of light, we must expand our view beyond the narrow slice of the electromagnetic spectrum that our eyes can see. The visible light that has guided our understanding of the universe for centuries represents less than 1% of all the electromagnetic radiation that fills the cosmos. To see the universe as it truly is, we must learn to see with radio eyes and infrared vision, to detect the whispers of microwaves and the shouts of X-rays, to perceive the full electromagnetic symphony that plays across the cosmos. At the longest wavelengths, stretching from meters to kilometers, radio waves carry some of the most important messages in the universe. These low-energy photons can travel vast distances through space without being absorbed or scattered, making them ideal messengers from the most distant reaches of the cosmos. Radio telescopes on Earth routinely detect signals from galaxies billions of light years away, their radio emissions providing crucial information about the structure and evolution of the universe. Some of the most important radio waves in the cosmos come not from distant galaxies, but from the universe itself. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate a persistent background noise from their radio antenna when they made one of the most important discoveries in the history of science. The noise they were hearing was not interference from their equipment, but the afterglow of the Big Bang itself, the cosmic microwave background radiation that fills all of space. This cosmic microwave background represents the oldest light in the universe, photons that were released when the cosmos was only 380,000 years old and had cooled enough for the first atoms to form. At that moment, the universe became transparent to light for the first time, and these ancient photons began their journey across space. Over the billions of years since then, the expansion of the universe has stretched these photons from their original high-energy state to the microwave radiation we detect today. The discovery of the cosmic microwave background provided the strongest evidence for the Big Bang theory and opened up an entirely new way of studying the early universe. By carefully mapping the tiny variations in this background radiation, astronomers have been able to trace the seeds of structure that would eventually grow into the galaxies and galaxy clusters we see today. In a very real sense, the cosmic microwave background is a baby picture of the universe, showing us what the cosmos looked like when it was just beginning to take shape. Moving to shorter wavelengths, we encounter infrared radiation, the heat signature of the universe. Every object with a temperature above absolute zero emits infrared light, from the warm glow of planets to the heat radiated by dust clouds in space. Infrared astronomy has revolutionized our understanding of star formation, revealing the hidden nurseries where new stars are born, within dense clouds of gas and dust that are opaque to visible light but transparent to infrared radiation. The Spitzer Space Telescope and its successor, the James Webb Space Telescope, have used infrared vision to peer through these cosmic dust clouds and witness the birth of stars and planetary systems. They have shown us that star formation is not a rare event, but a continuous process happening throughout the galaxy, with new stars being born at a rate of about 1 per year in our Milky Way alone. Infrared astronomy has also revealed the presence of brown dwarfs, failed stars that never quite accumulated enough mass to ignite nuclear fusion in their cores. These dim objects, glowing only with the heat of their gravitational contraction, are invisible to optical telescopes, but shine brightly in infrared light. The discovery of brown dwarfs has helped astronomers understand the full spectrum of stellar masses and the processes that govern star formation. At the short wavelength end of the infrared spectrum, we find the thermal radiation from planets and moons in our own solar system. Every world, from the scorching surface of Venus to the icy moons of Jupiter, tells its story through the infrared light it emits. By studying this thermal radiation, astronomers can determine surface temperatures, atmospheric compositions, and even weather patterns on distant worlds. The visible light spectrum, though narrow, remains the most familiar and perhaps most beautiful part of the electromagnetic spectrum. This is the light that has shaped our understanding of the universe for millennia, from the ancient observations of stellar positions to the modern spectroscopic analysis that reveals the chemical composition of distant stars and galaxies. Visible light astronomy reached new heights with the launch of the Hubble Space Telescope, which has provided us with some of the most stunning and scientifically important images in the history of astronomy. Free from the blurring effects of Earth's atmosphere, Hubble has revealed the universe in unprecedented detail, from the intricate structure of nearby planetary nebulae to the most distant galaxies visible in the cosmos. One of Hubble's most important contributions has been the discovery that the universe is not only expanding, but that this expansion is accelerating. By studying the light from distant supernovae, astronomers found that these stellar explosions appear dimmer than expected, indicating that they are farther away than they should be if the universe were expanding at a constant rate. This discovery led to the realization that some mysterious force, dubbed dark energy, is driving the accelerated expansion of the universe. The visible light from stars also carries detailed information about their chemical composition through the process of spectroscopy. When starlight is spread out into its component colors, it reveals a pattern of dark lines where specific wavelengths have been absorbed by elements in the star's atmosphere. Each element produces its own unique pattern of spectral lines, allowing astronomers to determine not only what elements are present in distant stars, but also their relative abundances. This spectroscopic analysis has revealed that the universe has been steadily enriching itself with heavy elements over cosmic time. The first stars, formed from the primordial hydrogen and helium, created in the Big Bang, contain virtually no heavy elements, but as these stars lived and died, they cooked up heavier elements in their nuclear furnaces and scattered them into space through stellar winds and supernova explosions. Successive generations of stars incorporated these heavy elements, gradually building up the chemical complexity that would eventually make planets and life possible. Moving beyond visible light to shorter wavelengths, we enter the realm of ultraviolet radiation, a form of light that is largely blocked by Earth's atmosphere, but reveals crucial information about the hottest and most energetic processes in the universe. Ultraviolet astronomy, conducted by space-based telescopes, has shown us the universe as a place of incredible violence and beauty, where massive stars burn with surface temperatures of 50,000 degrees or more, and where the space between galaxies is filled with hot, ionized gas heated by the ultraviolet radiation from countless stars. The ultraviolet light from hot young stars plays a crucial role in shaping the structure of galaxies and the space between them. This high-energy radiation can ionize hydrogen gas across vast regions of space, creating glowing nebulae that can be seen across millions of light years. The most massive stars produce so much ultraviolet radiation that they can ionize the entire interstellar medium of their host galaxies, creating bubbles of hot gas that can extend for thousands of light years. Ultraviolet astronomy has also revealed the presence of hot gas in the halos of galaxies, material that has been heated to millions of degrees by supernova explosions and stellar winds. This hot gas represents a significant fraction of the normal matter in the universe, and its discovery has helped solve the mystery of the missing baryons, ordinary matter that was predicted to exist by Big Bang nucleosynthesis, but had not been directly observed. At even shorter wavelengths, we encounter X-rays, electromagnetic radiation so energetic that it can only be produced by the most extreme conditions in the universe. X-ray astronomy has revealed a cosmos filled with violence and exotic objects that challenge our understanding of physics itself. X-ray telescopes have discovered that the space around black holes is filled with matter heated to temperatures of hundreds of millions of degrees as it spirals inward toward the event horizon. This superheated material shines brilliantly in X-rays, making black holes some of the brightest objects in the X-ray sky despite their reputation for trapping light. The study of X-ray emission from black holes has provided crucial evidence for their existence and helped astronomers understand how these exotic objects grow and influence their surroundings. X-ray astronomy has also revealed that galaxy clusters, the largest gravitationally bound structures in the universe, are filled with hot gas at temperatures of tens of millions of degrees. This intracluster gas, heated by the gravitational energy released as galaxies fall into the cluster, contains more mass than all the stars in all the galaxies in the cluster combined. The X-ray emission from this hot gas provides a way to measure the total mass of galaxy clusters, including the dark matter that makes up most of their mass. Neutron stars, the collapsed cores of massive stars, are another source of intense X-ray emission. These incredibly dense objects, with masses greater than the Sun compressed into spheres only 20 kilometers across, have magnetic fields trillions of times stronger than Earth's. As material falls onto the surface of a neutron star, it is heated to such extreme temperatures that it emits X-rays. Some neutron stars, called pulsars, spin rapidly and beam X-rays into space like cosmic lighthouses, their pulses arriving at Earth with clockwork precision. At the highest energies, we find gamma rays, the most energetic form of electromagnetic radiation in the universe. Gamma ray astronomy has revealed some of the most violent and exotic phenomena in the cosmos, from the annihilation of matter and antimatter to the acceleration of particles to energies that dwarf anything achievable on Earth. Gamma ray bursts, brief but incredibly intense flashes of gamma radiation, are among the most energetic events in the universe. These cosmic explosions, lasting from milliseconds to minutes, can release more energy than our Sun will produce in its entire lifetime. The discovery that gamma ray bursts occur in distant galaxies, billions of light years away, means that they must be incredibly powerful to be visible across such vast distances. The study of gamma ray bursts has revealed that they come in two main types: short bursts lasting less than 2 seconds, which are thought to be caused by the collision of neutron stars, and long bursts lasting more than 2 seconds, which are associated with the collapse of massive stars into black holes. Both types of events represent the death throes of stars, the final moments when stellar matter is compressed to such extreme densities that space and time themselves are warped. Gamma ray astronomy has also revealed that our own galaxy is filled with high-energy processes that are invisible to optical telescopes. The center of the Milky Way, hidden behind dense clouds of dust, shines brightly in gamma rays, revealing the presence of a supermassive black hole surrounded by hot, turbulent gas. Gamma-ray telescopes have also detected the signatures of cosmic ray particles, atomic nuclei accelerated to nearly the speed of light by supernova shock waves and other violent processes. But perhaps the most intriguing gamma-ray sources are the blazars, distant galaxies whose supermassive black holes are shooting jets of particles directly toward Earth at nearly the speed of light. These cosmic particle accelerators can boost electrons and protons to energies millions of times greater than anything achievable in terrestrial particle accelerators, creating gamma rays with energies so high that they challenge our understanding of fundamental physics. The full electromagnetic spectrum, from the longest radio waves to the highest energy gamma rays, represents humanity's window into the cosmos. Each wavelength of light carries its own unique information about the universe, revealing different aspects of cosmic phenomena that would remain hidden if we observed only invisible light. Radio waves show us the large-scale structure of the universe and the afterglow of the Big Bang. Infrared radiation reveals the birth of stars and the thermal glow of planets. Visible light provides the detailed spectroscopic information that tells us about stellar compositions and galactic motions. Ultraviolet light shows us the hottest stars and the ionized gas between galaxies. X-rays reveal the violent processes around black holes and in galaxy clusters. Gamma rays expose the most energetic events in the cosmos. Together, these different forms of light create a comprehensive picture of the universe that is far richer and more complex than what we could see with our eyes alone. They show us a cosmos that is dynamic and evolving, filled with processes that operate on scales from the subatomic to the cosmic, and across time spans from microseconds to billions of years. But the journey of light through the universe is not just about the sources that produce it or the telescopes that detect it. It is also about the medium through which light travels, the vast expanses of space that separate the stars and galaxies. For most of human history, we thought of space as empty, a perfect vacuum through which light could travel unimpeded. But modern astronomy has revealed that space is far from empty, filled with gas and dust, magnetic fields and gravitational waves, dark matter and dark energy. The space between stars in our galaxy contains a thin but measurable density of gas and dust, the interstellar medium that serves as both the graveyard of dead stars and the nursery of new ones. This interstellar material can absorb and scatter light, particularly at shorter wavelengths, causing distant stars to appear redder and dimmer than they would in a perfect vacuum. The study of interstellar extinction, as this effect is called, has revealed the distribution and composition of matter throughout our galaxy. Interstellar dust grains, tiny particles of carbon and silicon compounds, not only absorb starlight, but can also re-emit it at longer wavelengths, particularly in the infrared. This reprocessing of starlight by interstellar dust creates a diffuse infrared glow that permeates the galaxy, a reminder that space is filled with the debris of stellar evolution. The space between galaxies, once thought to be truly empty, has also been found to contain significant amounts of matter. the intergalactic medium, heated to millions of degrees by the gravitational energy of cosmic structure formation, contains more ordinary matter than all the stars in all the galaxies combined. This hot gas is largely invisible to optical telescopes, but can be detected through its X-ray emission and its absorption of light from distant quasars. Even more mysterious is the dark matter that makes up most of the matter in the universe. This invisible substance, which interacts with ordinary matter only through gravity, shapes the large-scale structure of the cosmos and determines the formation and evolution of galaxies. While dark matter does not emit, absorb, or scatter light directly, its gravitational effects can bend the paths of light rays through a process called gravitational lensing, allowing astronomers to map its distribution throughout the universe. Perhaps most mysterious of all is dark energy, the unknown force that is driving the accelerated expansion of the universe. This cosmic repulsion, which makes up about 70% of the total energy density of the universe, affects the propagation of light across cosmic distances. Light from the most distant galaxies has been stretched to longer wavelengths by the expansion of space itself, shifting visible light into the infrared and infrared light, into the microwave region of the spectrum. The journey of light through this complex cosmic medium is not just a passive process of transmission from source to observer. Light carries information about everything it encounters along the way, from the composition of stellar atmospheres to the density of intergalactic gas, from the strength of magnetic fields to the curvature of space-time itself. Each photon that reaches our telescopes is a messenger that has traveled across vast distances and cosmic time, carrying within it the story of its journey through the universe. But the most remarkable part of light's cosmic journey may be its final destination, the human eye and brain, where electromagnetic radiation is transformed into the experience of vision, where the objective reality of photons becomes the subjective experience of seeing. This transformation from the quantum mechanical properties of light to the neural processes of perception represents one of the most profound mysteries in all of science. The human eye is an extraordinary detector of light, capable of responding to individual photons under ideal conditions. The retina contains two types of photoreceptor cells: rods, which are exquisitely sensitive to light, but cannot distinguish colors, and cones, which are less sensitive but can detect the different wavelengths that we perceive as colors. When a photon strikes a photoreceptor cell, it triggers a cascade of chemical reactions that ultimately generates an electrical signal that travels along the optic nerve to the brain. But the eye is more than just a detector. It is also a sophisticated optical instrument that focuses light and processes visual information. The cornea and lens work together to form sharp images on the retina, while the iris controls the amount of light entering the eye. The retina itself performs complex processing of visual information, with different types of cells responding to edges, motion, and color contrasts. Recent research has shown that the human visual system is even more remarkable than previously thought. Experiments have demonstrated that humans can detect single photons under carefully controlled conditions, pushing the limits of vision to the very edge of what is physically possible. This extraordinary sensitivity means that when you look up at a faint star on a clear night, individual photons that began their journey in a nuclear furnace light years away are triggering responses in your retinal cells. The transformation of light into vision involves not just the eye, but the entire visual processing system of the brain. The electrical signals from the retina are processed by a complex network of neurons that extract information about edges, shapes, colors, and motion. This neural processing creates the rich visual experience that we take for granted, transforming the objective reality of electromagnetic radiation into the subjective experience of seeing. But human vision, remarkable as it is, represents only a tiny fraction of the electromagnetic spectrum. We have evolved to see the narrow band of wavelengths that penetrate Earth's atmosphere and are abundant in sunlight, but we are blind to the vast majority of the light that fills the universe. To truly see the cosmos, we have had to extend our vision with instruments that can detect radio waves and infrared radiation, ultraviolet light and X-rays, gamma rays and gravitational waves. These instruments, from radio telescopes to space-based observatories, serve as extensions of human perception, allowing us to see the universe in ways that our biological evolution never prepared us for. They reveal a cosmos that is far stranger and more wonderful than anything visible to the naked eye, filled with phenomena that challenge our understanding of physics and our place in the universe. The story of light is ultimately the story of information, of how the universe communicates with itself across vast distances and cosmic time. Every photon carries within it the signature of its birth, whether in the nuclear furnace of a star, the accretion disk around a black hole, or the quantum fluctuations of the early universe. This information travels at the ultimate speed limit of the cosmos, crossing billions of light years of space to reach our telescopes and our eyes. When we look up at the night sky, we are not just seeing distant suns and galaxies. We are receiving messages from across the universe, communications that have been traveling toward us for millions or billions of years. The light from the most distant galaxies carries news of the universe when it was young, when the first stars were forming, and the cosmic web of structure was just beginning to take shape. In this sense, astronomy is fundamentally an act of communication, a conversation between humanity and the cosmos, conducted in the language of light. Every observation, every photograph, every spectrum is a message decoded from the electromagnetic radiation that fills the universe. And in learning to read these messages, we have discovered not just the nature of stars and galaxies, but the fundamental laws that govern reality itself. The quantum nature of light, revealed through experiments like the photoelectric effect and the double-slit experiment, has shown us that the universe operates according to principles that defy our everyday intuition. Light can behave as both wave and particle, existing in multiple states simultaneously until the moment of observation collapses it into a single reality. This quantum behavior is not just a curiosity of physics laboratories. It is the fundamental nature of reality itself, governing everything from the fusion reactions in stellar cores to the chemical processes that make life possible. The wave-particle duality of light has profound implications for our understanding of the universe, our place within it. It suggests that the act of observation plays a fundamental role in determining the nature of reality, that the universe is not a collection of objects, with definite properties existing independently of observers, but rather a web of possibilities that become actualized through the process of measurement and observation. This quantum nature of light also underlies many of the technologies that have revolutionized our understanding of the cosmos. Lasers, which produce coherent beams of light with precisely defined wavelengths, have enabled new forms of spectroscopy that can detect the faintest traces of elements in distant stars. Charge-coupled devices which convert photons into electrical signals with extraordinary efficiency have made it possible to detect individual photons from the most distant galaxies. Quantum sensors, which exploit the wave-like properties of light, promise to open up new windows on the universe with unprecedented sensitivity. But perhaps the most profound implication of the quantum nature of light is what it tells us about the fundamental interconnectedness of the universe. Quantum entanglement, the phenomenon by which particles can be correlated across vast distances, suggests that the universe is not a collection of separate objects, but a unified whole in which every part is connected to every other part. The photons that carry information across the cosmos are not just messengers traveling through empty space, but manifestations of the underlying quantum field that permeates all of reality. This interconnectedness extends beyond the realm of physics to touch on some of the deepest questions about consciousness and the nature of experience. The transformation of light into vision, the process by which electromagnetic radiation becomes conscious perception, remains one of the great mysteries of science. How does the objective reality of photons become the subjective experience of seeing? How does the brain construct the rich visual world that we experience from the sparse information carried by light? These questions touch on the hard problem of consciousness, the mystery of how physical processes in the brain give rise to subjective experience. While we understand in great detail how photons are detected by the retina and how visual information is processed by the brain, the leap from neural activity to conscious perception remains unexplained. Some researchers have suggested that quantum effects in the brain might play a role in consciousness, though this remains highly speculative. What is clear is that the journey of light from distant stars to human consciousness represents one of the most remarkable processes in the universe. A photon born in the nuclear furnace of a star, traveling for years or centuries through the vacuum of space, finally arrives at a human eye where it triggers a cascade of chemical and electrical events that ultimately result in the conscious experience of seeing starlight. In that moment, the universe becomes aware of itself, matter contemplating matter across the vast expanses of space and time. This awareness, this ability to decode the messages carried by light, represents perhaps the most remarkable achievement of evolution on Earth. Through billions of years of natural selection, life has developed the ability to detect and interpret electromagnetic radiation, to extract information from the quantum mechanical properties of photons, to see the universe and understand its workings. We are, in a very real sense, the universe becoming conscious of itself. matter organized in such a way that it can contemplate its own existence and origins. The story of light is far from over. New technologies and new discoveries continue to expand our understanding of electromagnetic radiation and its role in the cosmos. Gravitational wave detectors have opened up an entirely new window on the universe, allowing us to detect the ripples in space-time itself, produced by colliding black holes and neutron stars. These gravitational waves carry information about the most extreme conditions in the universe, complementing the electromagnetic radiation that has been our primary source of astronomical information. Future space telescopes will push the boundaries of what we can see even further, detecting light from the very first stars and galaxies that formed in the early universe. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is already revealing galaxies that formed when the universe was less than 1 billion years old, showing us how the cosmic web of structure first began to take shape. New technologies for detecting and manipulating light at the quantum level promise to revolutionize our understanding of the universe. Quantum computers, which exploit the wave-like properties of particles to perform calculations impossible with classical computers, may help us solve some of the deepest mysteries of cosmology and fundamental physics. Quantum communication systems, which use the entanglement properties of photons to transmit information with perfect security, may one day allow us to communicate across interstellar distances in ways that are fundamentally secure. But perhaps the most exciting prospect is the possibility of detecting life on other worlds through the light they emit or reflect. The study of exoplanet atmospheres, conducted by analyzing the starlight that passes through them, has already revealed the presence of water vapor, methane, and other molecules that could be signs of life. Future telescopes may be able to detect the spectroscopic signatures of photosynthesis, the process by which life on Earth harnesses the energy of sunlight to build complex molecules from simple ingredients. The detection of life on other worlds would represent the ultimate vindication of the power of light as a carrier of information across the cosmos. It would show that the same electromagnetic radiation that reveals the composition of distant stars and the structure of galaxies can also carry the most precious information of all, the signature of life itself, the indication that we are not alone in the universe. As we stand on the threshold of these new discoveries, it is worth reflecting on how far we have come in our understanding of light and its role in the cosmos. From the ancient Greeks, who first recognized that light travels in straight lines, to Newton and Huygens, who debated its nature as particle or wave, to Einstein and Planck, who revealed its quantum character, to the modern astronomers who use it to probe the deepest mysteries of the universe. The study of light has been central to our growing understanding of reality itself. The journey of a single photon from a distant star to your eye encapsulates the entire history of the universe, from the Big Bang that created the fundamental particles and forces, to the formation of the first stars and galaxies, to the evolution of life on Earth and the development of consciousness capable of contemplating its own existence. In that moment when starlight enters your eye, you are connected to the cosmos in the most direct way possible, participating in the ongoing conversation between matter and energy, between the universe and itself. This is the true wonder of light, not just that it illuminates the world around us, but that it connects us to the deepest mysteries and most profound truths about the nature of reality. Every photon that reaches us carries within it the story of the cosmos, the history of matter and energy across billions of years of cosmic evolution. In learning to read these stories, in decoding the messages carried by light, we have discovered not just the nature of stars and galaxies, but the fundamental principles that govern the universe itself. The mystery of light continues to unfold, revealing new wonders and new questions with each passing year. As we develop new technologies and new ways of seeing, we will undoubtedly discover phenomena that we cannot yet imagine, aspects of the electromagnetic spectrum that will challenge our understanding and expand our conception of what is possible. But one thing remains constant. Light will continue to be our primary messenger from the cosmos, our window into the deepest truths about the nature of reality and our place within it. So the next time you look up at the stars, remember that you are not just seeing distant suns, but receiving messages from across the universe, communications that have been traveling toward you for years, centuries, or millennia. Each photon that enters your eye is a quantum messenger carrying news of nuclear fusion and stellar evolution, of the birth and death of stars, of the expansion of the universe, and the formation of cosmic structure. In that moment of seeing, you become part of the cosmic conversation, a conscious participant in the universe's ongoing attempt to understand itself. This is the ultimate meaning of light, not just electromagnetic radiation propagating through space, but information itself, the medium through which the universe communicates its deepest secrets and most profound truths. In learning to see with all forms of light, from radio waves to gamma rays, we have learned to hear the universe speaking to us in its own voice, telling us the story of where we came from, how we got here, and what our future might hold among the stars.